first of all, I would like to thank Alexandre for inviting me here to also to present, to give me the possibility to present these results that we have obtained on study of IV characteristics, non-linearity in IV characteristics in several systems and superconducting systems. We used actually this study to make some prediction about the possibility to use materials. The idea was to make prediction to use materials as superconducting single photon detectors, actually. Okay, so it's better know that I will not go into details here, that high velocity of flux in superconducting materials is a very important topic also from fundamental, from applicative point of view. Alexander tomorrow will give will give a talk, I think, on magnonics, spintronics, and fluxonics. But here, the idea, as I said, was to study the fast dynamic of fluxons to determine the mechanism which, plays an important role now in superconducting single photon detectors where they are, let's say, they have micrometer dimensions. Also, in the case of superconducting nanowire single photon detectors, which are completely based on different mechanism of detection. Let's say the main important point is related to the electron phonon scattering length, which is related to electron phonon coupling time tau 0, which is of course not directly connected to the time to the quasi-particle relaxation time that we measure, we detect from IV characteristics, from these instabilities in the IV characteristics, but the scaling between these two quantities it's quite robust in the sense that low values of the inelastic scattering time will typically give low electron phonon coupling time in the material. Okay. Here. Okay, so from the instability, from the study of the instability in the IV curves, we can have information about the critical velocity of the vortices V star, which is related to this time tau e, which is the inelastic relaxation time of the quasiparticles. And from these numbers, we can make some prediction about the possibilities, I said, to use materials as superconducting quantum single photon detectors. Also, the temperature dependence. We should be trained before. Okay. Okay, so let's go here. So also the temperature dependence, as I said, will give us of tau, will give information about the mechanism which is in play in the dissipation in the quasiparticle vortex, in the quasiparticle relaxation time. So if the interaction is mainly due to electron phonon, tau goes like a power of -3 with the temperature. If in the case of electron-electron scattering, the dependence is more exponential. So from these two temperature dependence, you can also understand what's going on, what's the main relevant mechanism of dissipation in the quasiparticles. So here. Okay, so all the results which I will present here, a very easy system. So all the films and the systems have been deposited by UHV sputtering system, and also the geometry is very simple. So just order of 10 micrometer wide strip, and the thickness of the sample of the films goes between 10 and 30. Sometimes they are thinner, but I will show. I will explicitly say when this is the case. Okay, so I want just now to start from the end. So in the sense that this was some final results that we obtained some years ago on a new materials, which is niobium rhenium. These are the only films which are around of this non-centrosymmetric superconductor, which we started to use for different purposes. But the most important features of this superconductor is that it has a very short coherence length of the order of 4 nanometers, which means that you can have quite high TC also for very thin niobium rhenium films. In our case, we get something around a bit higher than 5K for 3 nanometer thick films. Also, the resistivity is quite high. So already these two characteristics makes this material appealing for superconducting single photon detectors. So, but the question that we asked ourselves was, what is the critical velocity? So what's the time, the inelastic relaxation time connected, which associated to this material? And actually, you see we end up with a quite high 1 kilometer per second critical velocity, so a tau, an inelastic scattering time, which was of the order of 200 picoseconds. So, okay, someone in Delft read this paper, and they say, okay, maybe we can try to build real single photon nanowire superconducting single photon detectors. They did, and the results were quite encouraging. This is the experiment was done on 8 nanometer thick films, and let's say what was nice for us that the time, so especially the recovery time and also the time jitter for this system was quite low, and they were comparable to other performances, that have been obtained on the materials which were very, very established material for superconducting single photon detectors, like niobium, titanium nitride, or amorphous tungsten silicide. So even though the two times, as I said, were not directly connected, this was for us a good indication that we were going in the right direction. Yes. So also, this is still unpublished, the results, very recent. Maybe this is even more important because this experiment have been done on the niobium rhenium thin films of 4 nanometer thick on a white, so this is a microstrip superconducting single photon detectors, and you can see here that we have been able to detect single photons. So I say this for us is much more important because this is a very easy geometry. So I mean, you don't need to go to Delft to convince people that they have to do very, let's say, advanced things. So this is for a study of feasibility. It's for us is very important. And as I said, there are still unpublished results. So this is the beginning. So we started, let's say, 15 years ago, and we started to measure these IV characteristics, so this sudden jump in the IV curves and of niobium, which is okay, the material that we know very well, and we asked ourselves what is going to happen if we put a ferromagnet on the top of the superconductor, and we started with put let's say the stronger ferromagnet iron, and actually didn't happen, nothing. So we measured a lot of samples, a lot of bilayers, niobium iron. We changed, here is a 40 nanometers iron, 25 nanometers thick niobium, but we changed a lot of thickness, a lot of combinations. We always end up with the same critical velocity. Maybe this can be due or bad interface transparency between the two materials, or also to the fact that the superconductivity, the penetration depth of the superconductivity in the iron is very, very low. So actually you always probe only niobium. In fact, also the temperature dependence of tau is exponential, like was, the feeling was that you were just measuring the properties of niobium. So then we say, okay, let's change the ferromagnet, so the strong ferromagnet, and we go to iron nickel, so the permalloy, and in this case, the results were much more better. You see here, we measured a critical velocity of 2 kilometers per second, and these are two samples, 10 and 20. Okay, niobium is always 25 nanometers, and permalloy is 10 and 75 nanometer, more or less the same value of the critical velocity. Here is the saturation, more or less the field when the critical velocity saturates. And from the value of V star, we can have some information, as I said, on tau E. And in this case, tau, as you see, was 40 picoseconds. So, well, encouraging at that time was an encouraging result. In both cases, the temperature dependence of the relaxation time was exponential. In the case of niobium, okay, this is tau here, okay, the factor m here equals 2, as it as it should be, because okay, niobium is typical BCS superconductor. In the case of permalloy, we have also an exponential behavior, but with m equal 1, so a sort of reduced gap in the average, the system experience the quasi-particle reduced gap in the system. And maybe with respect to the niobium iron, we have, of course, a smoother decay of the order parameter in the permalloy, because the penetration of the superconductivity is longer, because permalloy is, let's say, is strong, but it's weaker ferromagnet with respect to iron. But still, the superconducting, the coherence, the penetration depth of the superconductivity in the ferromagnet is very small, 1-2 nanometers. But here was what I think was most interesting results on permalloy. Well, 10 years later, we studied the influence of the magnetic configuration of permalloy on the critical velocity. So we prepared 3 samples which were characterized by different magnetic configuration of in the permalloy. So one which was whose thickness was similar to the previous one, 50 nanometers. So in which the magnetization is always in plane, and other 2 which, I will not going into details here, but in these 2 cases, the magnetization as a component out of the plane, so which is going up and down. So stripes develops in the system, and we measured the IV curves in the 3 cases. Here is the critical temperature. The critical temperature is the critical current. The critical current is almost the same for the 3 samples, but what we got was a completely different situation for the critical velocity. And here, these 2 red curves are the most important results, I think. First, very high value of the critical velocity, something about 4 or 5 kilometers per second. I should also say that in this case, niobium was deliberately fabricated as a dirty, this niobium was dirtier than the previous one, so also this maybe plays a role in the, not maybe, this for sure plays a role in increasing the critical velocity. But as I said, the most important thing is the result is this. These 2 curves are, the red ones are measured on the same niobium permalloy bilayers. This is 200 nanometers thick. The red points are when the sample is in the homogeneous state, and here is when stripes are created in the systems. And you can see that you have an increase of the critical velocity, so a decrease of the time relaxation time, which is clearly related to the inhomogeneous nature of the magnetic configuration, because since JC is the same in all the hybrids, we ascribe this behavior to the different magnetic configuration, which here is homogeneous, and here is homogeneous, and here is inhomogeneous. And you can see here that we have relaxation time of the order of few picoseconds. I will not go into details. We made a lot of other, study a lot of other materials. Now we pass to weak ferromagnets, niobium, palladium, nickel. For example, here is critical velocity for niobium, and here is for niobium, palladium, nickel. And again, increase of the critical velocity. all these samples are always prepared in the same deposition run. So, I mean, niobium, the quality of niobium here is exactly the same than here. And you see, higher critical velocity. Okay, well, this is the mechanism. Okay, also the same with, yes, this niobium copper nickel, and again this is niobium and higher critical velocity for niobium copper nickel, and in niobium copper nickel the critical velocity is even higher with respect to niobium to palladium nickel, because okay, they are both weak ferromagnets, but copper nickel is more disordered because, and his resistivity is higher, and this gives us a critical velocity which is higher in this case. Also, the relaxation mechanism is completely different, almost constant value of behavior of tau as a function of the temperature, which is also could be interesting for superconducting single photon detectors, because then the relaxation time is more or less fixed as a function of the temperature, so they can operate more or less. I mean, this is at the same temperature. Okay, also we this with the niobium nitride copper nickel. This is a more complicated, let's say, layout of the sample that we measured. We have these phase leaps here, but we just concentrate on the first jump at lower current, and we also obtain the same result. So as you say, you see here, this is, yes, again, niobium, nitride, and higher velocity niobium nitride copper nickel. So when you put a ferromagnet on the top of your superconductor, we always see an increase of the critical velocity. And okay, this is just to, but now what we want to do now is what we have done now. It was, since we obtained, real single photon superconducting single photon detectors have been made out of niobium rhenium, both nanowire and micrometer strip single photon detectors. We want to propose now what happens if we put copper nickel on the niobium rhenium. And then we fabricated this by layers. We measured critical velocity, and you see here again that the results are very encouraging. So the critical velocity is more or less, 2 times of in the case of niobium rhenium copper nickel with respect to the niobium rhenium, and also I think more, maybe 4 times. And also the relaxation time is, it's 1 order of magnitude smaller. So I think I should end up with the conclusion. Yeah, we have done also, okay, now this is also interesting. I think we also sputter different materials. So niobium rhenium nitride. So also these are the only few, these are the only films which are around. So the idea was to make niobium rhenium even dirty. So, say the same, follow the same route, niobium to niobium nitride, and going from niobium rhenium to niobium rhenium nitride for detectors. But in this case, we did not see, at least until now, a decrease of the critical velocity, or a decrease of the inelastic scattering time, which is almost the same as a niobium rhenium. Okay, we have done different experiments. So I have shown just an overview of a lot of materials combination, superconductors, strong, weak ferromagnets, niobium rhenium, and what is good for us is that finally detection experiments have been really and concretely performed on superconducting narrow-wire single photon detectors and microstrip superconducting single photon detectors made out from niobium, which confirms our prediction. Of course, our plan now is to go into the direction to do something which is hybrid which contains a ferromagnet. So we want to propose to make some detectors with niobium rhenium permalloy, or maybe better, I think, niobium rhenium copper nickel. Okay.
So this presentation is now open for discussion. Thank you for your presentation. Are there any questions, comments?
Yes, please.
Yes, I'm sorry I missed the first couple of minutes. So, what is your method to determine the timescales? Because I mean, you're not doing any ultra-fast spectroscopy in real time, etc. Right?
Yeah, the message is very easily, with a very easy experiment, you can have indication about the possibility, of course, to use materials, just as a first check, to use materials as possible candidates as superconducting single photon detectors.
No, but the question is, how do you estimate the time scales? 5 picosecond, 20 picoseconds. How do you do that?
From the Larkin-Ovchinnikov, yes. Okay, from the Larkin-Ovchinnikov, I measured the critical velocity, and from that formula I get out from. Yes.
Okay.
That's all.
Okay.
And I said that, of course, there are completely different mechanisms, whatever, but the scaling between these two times is quite robust, at least in our experience. And I mean, you can have indication. In fact, from Delft, I mean, they just saw this paper and say, okay, let's try, and it worked. Of course, I should also say that in the experiment of Delft, I mean, they did not optimize the electronics, they did optimize the geometry, they did not optimize the design. So the numbers that they got, they were not ideal, I think. They can go ahead, but of course they do with the niobium nitride, niobium titanium nitride, and they don't want to do this. Okay?
Thanks.
Any other questions? So if no question,
maybe just a brief comment from my side. So it seems that like your NbReN material looks as a quite highly performant, so good material indeed for detection.
Yes.
But you working with different geometries in terms of the width of your microstrips.
Yes.
So I mean that the recent studies reveal that also the type of edge
Sure.
Might affect the nucleation of vortices and so on. So it would be interesting to take a closer look
you're right.
at the quality of your
Yeah,
edges.
you're right,
Maybe you could even improve
Yes.
if you suppress the nucleation of instability
No, you're
on
right.
the edge.
But you're perfectly right. Then this one, where is it? No. This, yeah, sure. These are the ongoing experiments. We are changing the width of the stripes, and then we would do a systematic study, of course. So this is done on niobium rhenium nitride in any case. But the idea is just as you said. I mean, we have also to see
and
this.
For which widths have you already evidenced the single photon nature of response?
1.3 nanometers.
Okay, so it's already microstrips.
Yeah.
So very good.
Yeah, this is already. Okay, but we want to do as a function of the, as I said, what is it?
Okay, so thank you very much.
Okay.
Yeah.
Okay, thank you. Thank you.